Now, sometimes you're dealing with data where extremely large values are not outliers. They're actually systematic, so they occur time and time and time again. There are lots of examples of that. A really good example is personal wealth. Right? So if you take all the individuals in the world and plot a histogram of the personal wealth, there will be people with very, very large wealths, and they are effectively outliers because they skew the numbers tremendously. Right? If somebody's worth tens of billions of dollars or pounds, that puts everything out of proportion. Everyone else's net worth looks strange and silly. But the problem is you cannot treat those individuals as outliers because they're not. Right? The fact that somebody has $100 billion in the bank doesn't mean that somebody accidentally stuck a few zeros in the end. There are actually real people with that much money. So they are extreme values, but they're systematic. They occur all over the place. And if you take that individual and remove them from the data set, there will be another individual with a similarly high net worth, with a similarly high value. So you cannot remove them as outliers, but you still have to do something, because if you take net worth just normally and put it into a learning algorithm, you will end up with a highly skewed distribution of numbers, and your algorithm is not going to work properly, because basically the guy who makes $10,000 a year and the guy who makes $1 million a year, they're going to look identical compared to the guy who makes 10 billion. Right? It's all a question of scale. So you can't remove them as outliers, but what you have to do is you have to somehow de-skew the distribution of values. So the extreme values, they affect different learning algorithms to a different degree. So they affect, for example, they affect regression heavily. They affect nearest neighbor methods. Decision trees are almost immune to them, interestingly. So we'll talk in detail about why when we cover those methods. So how can you fix that? Well, the simple fix, so for something like net worth, you just put it on log scale, right? So instead of taking the original values, you take logs of them. Logs only work for positive numbers. If you have positive and negative numbers with extreme values, then you can use something like an error function or an arctangent, basically something that will squash the whole range into a finite region, and then you normalize them, as I said on the previous slide. You can also use cumulative distribution functions. So basically, you rank things and use rank instead of the value. Another really interesting thing with numeric attributes is monotonicity of the effect that the attribute has on what you're trying to predict. So some attributes are monotonic, and it's not the attribute itself, it's the relation between the attribute and what you're trying to predict. So it's best to show it by example. So suppose you are a bank and you're trying to decide whether you want to give money to the person. So you're assessing their lending risk. Right? Now, if one of the attributes is net worth, then there is a monotonic relationship between net worth and the risk assigned to the individual. Basically, the richer they are, the lower the risk that they will default on the loan in general. So the relationship is pretty monotonic. And if the guy doesn't have anything, if he has a very small net worth, there is a higher risk associated with lending money. So the relationship is monotonic. Right? Monotonic relationships are good. And most of the algorithms that we have, they, in one way or another, assume that the relationship between the attribute and what you're predicting is monotonic. Right? An example of a non-monotonic relationship is, suppose you're trying to predict if somebody's going to win a marathon, or a race of some kind, and one of the attributes is age. Now, a 3-year-old is not going to win a marathon. And a 100-year-old person is not going to win a marathon either. But somewhere in the middle, there is an age where people are much more likely to win marathons. So what that means is the relationship is not monotonic. If you have very small values, the probability of winning is small. If you have very large age, the probability of winning is small. And then there is a sweet spot somewhere that makes it much higher, that gives a higher chance to winning. So that kind of a non-monotonic relationship is problematic for pretty much every algorithm that we'll talk about. So linear methods cannot handle it. Nearest neighbor methods are actually relatively immune, but not really. But lots of other methods are affected. So how do you fix something like that? There's an almost universal fix. You can discretize or quantize the data, right? So you have a numeric attribute, and what we're going to do is we're going to turn it into a categorical attribute, or more accurately, into an ordinal attribute. And the way we're going to do that is we're going to take the range and we're going to cut it up in a few regions, and we're basically going to quantize. Instead of using a number to represent an individual, we're going to use a category. Say he's under 20 or 20 to 50 or over 50. So now we have we have a categorical or ordinal attribute with three possible values. And that is something that a learning algorithm can pick up on and can basically learn that this is the group or the label that is most associated with winning a marathon. And these categories have a much lower chance of winning. So the neat thing about quantization is you can do it in a completely unsupervised manner. So you don't actually need to know what it is you're predicting. So you don't need to do a correlation between the chance of winning and the different and the different ages. What you can do is you can just take age and cut it up into uniform chunks, and most of the time you actually use half overlapping chunks. Right? So you slice it up in lots of different overlapping ways, and you end up with possibly a couple of categorical attributes or lots of binary attributes. So what you're doing is you're going from numeric attributes to discrete attributes in the hope of removing that monotonicity. And we'll see more examples in the course.